we now learn about position vectors and displacement vectors. And put simply, if you're studying vectors, then you need to know about these. Here's the whole idea. Consider the XY grid we can see on the right-hand side of the screen here, on which I've already plotted 2 points A and B, whose coordinates are shown here. Indeed, we can see that point A has coordinates 2, 5, and point B has coordinates 6, 3. And do keep in mind, by the way, that over here I haven't drawn anything to scale, so the points A and B that you see here are roughly where they'd be on the XY grid. Now, we'll start with position vectors, and in fact I'll go ahead and write that, position vectors. There we go. And put simply, given a point, such as the point A we have here, its position vector tells us the position of this point A relative to the origin. So that's the point O we have here. And in fact, if I go ahead and draw that vector, the position vector OA is the vector which starts at the origin, O, and finishes at point A. There we go. That's the position vector OA. And to write this position vector OA in component form, all we need are the coordinates of point A. Indeed, since the coordinates of A are 2, 5, the position vector OA will have components 2, 5. And hopefully that makes sense, since to get from this vector's tail to its head, starting from the tail, we'd move 1, 2 units to the right, and 5 units upwards. In a similar way, we could define the position vector of point B, so that would be the vector OB that I'm drawing right now. There we go. And I'll label that as well, OB. And again, this position vector OB tells us the position of point B relative to the origin. And so using the coordinates of point B, those are 6 and 3, we can quickly write the vector OB in component form as 6, 3. There we go. Now, position vectors like these are very important. Indeed, whether it be for problems in geometry or problems in engineering and physics, the fact that position vectors tell us the exact position of a point relative to an origin makes vectors like these particularly useful for modeling real-life situations. For now, though, the thing to take away from this tutorial is the fact that a position vector tells us the position of a point relative to the origin. Okay, now that that's said, how about displacement vectors? And I'll quickly write that as well, displacement vectors. Well, a displacement vector tells us how to get from one point to another. So for instance here, we could define the displacement vector AB, and in fact, I'll quickly draw that. The displacement vector AB would be the vector which starts at point A and finishes at point B. So that would be this vector right here. And I'll go ahead and label that. That's the vector AB, which we write like this. There we go. Okay, so this vector AB tells us how to get from point A to point B. But so how do we actually define this vector AB? Well, there are two ways really, and I strongly recommend you be comfortable with both. First of all, provided we have the coordinates of the points A and B, as we do here, there's a convenient formula we can use to define the vector AB. And here it is. If we know that point A has coordinates x sub A, y sub A, so the x and y coordinates of point A, and that point B has coordinates x sub B and y sub B, those are just the x and y coordinates of point B, then the vector AB will have components xb, so the x coordinate of B, minus xa, and yb minus ya. There we go. And in fact, I'll go ahead and box that formula. If we know the coordinates of the points A and B, this formula is definitely worth knowing. And so for the displacement vector AB that we see here, given the coordinates that we have at the top of the page, we can go ahead and state that the vector AB is equal to, well, let's see. The x component will be the x coordinate of B minus the x coordinate of A, so that will be 6 minus 2. And in fact, I'll write it out, that's 6 minus 2. And the y component will be the y coordinate of point B minus the y coordinate of point A. So that will be 3 minus 5. So I'll write that as well, that's 3 minus 5. There we go. Now, of course, since 6 minus 2 is 4 and 3 minus 5 is negative 2, we can go ahead and state that the displacement vector AB we have here, well, it has components 4, negative 2. And we're done. We've now defined the displacement vector AB. And again, what this vector tells us is that to get from this point A to this point B, or we could say that the position of point B relative to point A is 4 units to the right and 2 units downwards. So that's 4 units to the right and 2 units downwards. And so as such, that's what a displacement vector tells us. It tells us how to get from one point to another. It's worth pointing out, by the way, that any position vector, like the ones we have here, is therefore a displacement vector which always has the same starting point. That is, the origin. That being said, I carry on. Given we've also seen position vectors in this tutorial, it's worth pointing out, and in fact I feel it's important to know, that rather than working with the formula we have here, we could also define our displacement vector AB as a difference of two vectors. Indeed, since both of the position vectors OB and OA start at the origin, and since OB points towards the head of AB and OA points towards the tail, we can use our knowledge of subtraction with vectors to state that the displacement vector AB is equal to the position vector of B minus the position vector of A. Remember, given two vectors which are drawn from the same starting point, which is the case here, a subtraction like this one leads to the vector which tells us how to get from the head of the vector that's being subtracted to the head of the vector we're subtracting from. In other words, OB minus OA equals to the vector which tells us how to get from point A to point B, which is the vector AB we're trying to find. And trust me when I say that when working with vectors in geometry, this result is one that you definitely want to know. And so for the sake of showing you that this, of course, leads to the same result as the one we just found, using the position vectors of OA and OB that we found earlier, we can quickly state that the vector AB, that's the displacement vector from A to B, is equal to OB, which is 6, 3. So let me quickly write that. That's the vector 6, 3. Minus OA, which is 2, 5. So that's 2, 5. And of course that's equal to the vector whose x component is 6 minus 2 and whose y component is 3 minus 5, which quickly leads to the result, vector AB is equal to the vector with x component 6 minus 2, which is 4, and y component 3 minus 5, which is negative 2. There we go. And clearly, that's the same result as the one we found with our formula here. Okay, now there's another result I'd like to make sure you're aware of. And for that, let's say we had another point on our XY grid here, and I'll call it point C. And so let's say point C has coordinates 4, 7. And so very roughly speaking, point C would be somewhere up here. There we go. Now let's say we were asked to define the displacement vectors CA, which I'm drawing right now. There we go, that's vector CA, as well as vector CB, which I'm drawing right here. And I'll label that one as well. That's the displacement vector CB. There we go. And in fact, as a good exercise for you to do, you could go ahead and press pause and try defining these displacement vectors CA and CB using either one or both of the methods we've just seen here. And you should find that the displacement vector CA has components negative 2, negative 2, and the vector CB has components 2, negative 4. And I suppose I could also write the position vector of point C right here. Since C has coordinates 4, 7, its position vector OC, well, that will just have components 4, 7. There we go. So again, by all means, go ahead and press pause and try finding these two displacement vectors using both of the methods you see here. Either way, though, I'll carry on to the result I want to make sure that you know. Given any other point like the point C we've just seen here, we could also define this displacement vector AB as the difference of the vectors CB and CA. Indeed, the displacement vector AB is also equal to CB minus CA. And again, this result will be very useful for geometry problems involving vectors. And the important thing to remember here, really, is that a displacement vector like the vector AB we have here can be seen as a difference of any two vectors, provided those two vectors have the same starting point, so in this case it's C, and provided the vector that's being subtracted points towards the tail of the displacement vector we're trying to find, so in this case it has to point towards A, and the vector we're subtracting from needs to point towards its head, so in this case it's pointing towards B. Indeed, provided those conditions are met, we could define this displacement vector AB using any other point on this xy grid. So if I had a point D here, for example, and in fact I could add a point D right there, let's say I had a point D, then this vector AB could be defined as DB minus DA. Or say I had a point E, which is up here. Then this displacement vector AB could be defined as EB minus EA. It doesn't matter where the other point is, that result will always stand. So do make sure you're comfortable with it. Now let me quickly erase those. The D is gone and the E is gone. There we go. And now just to confirm this result with the components we have here, we can therefore state that the displacement vector AB is equal to CB minus CA, where CB is 2, negative 4. So let me quickly write that. That's 2, negative 4, minus the vector CA, which has components negative 2, negative 2. So that's negative 2, negative 2. And so this becomes the vector whose x component is 2 minus negative 2, and negative 4 minus negative 2. Now 2 minus negative 2 turns into 2 plus 2, which is just 4. And for the y component, we have negative 4 minus negative 2, so that's negative 4 plus 2, which is negative 2. And we're done. As we can see, once more, we get the same result. The displacement vector AB has components for negative 2. Okay, we're nearly done here. I just want to show you one or two more things, which I feel are definitely worth knowing. The first of which are opposite vectors. And in fact, I'll quickly write that here. I'll say opposite vectors. Opposite vectors. There we go. And put simply, if we have a displacement vector, such as AB that we have here, then the displacement vector which tells us how to get from point B to point A, so that would be the displacement vector BA, is the opposite of vector AB. Consequently, its components are the opposites of the ones we see here. More generally, though, we can say that if a vector AB, so that's a displacement vector AB, is equal to xy, then its opposite, so that would be the vector BA, will have components negative x, negative y. And in fact, I'll go ahead and box that. That's quite important, so you do want to make a note of that. And so using the displacement vector AB we have here with components 4, negative 2, we can state without further proof that BA is equal to negative 4, 2. And consequently, if we were to add the displacement vectors AB and BA, it will equal to the null vector, so that's 0 with an arrow on top, whose components are simply 0, 0. Okay, now that we've talked about opposite vectors, there's one more important thing I want to show you. And for that, I'll use the space that we have up here, and let me just make a separate box for what we'll be writing here. There we go. Now technically, what we're about to talk about here is addition with displacement vectors. And there's a convenient rule to know with displacement vectors, which is Chasles' rule. There we go. And essentially, this is the tail-to-head method with displacement vectors. And here's the whole idea. Let's say I have 3 points. I have a point A, and a point B, and a point C. And let's say I were to add the vectors AB and the vector BC. Then what Chasles' rule tells us, and in fact this S is part of the mathematician's surname, so there really should be an apostrophe on that S. There we go. And I'll carry on, sorry. What Chasles' rule tells us is that as we add this vector AB to this vector BC, then because we have the same letter on either side of this addition, indeed we have a B here and a B here, they technically cancel each other out and will be left with the displacement vector AC. And this result can be very convenient for geometry problems with vectors. For instance here, let's say we had been asked to find the displacement vector AC. So that's the displacement vector I'm hovering over right now. Then, according to this rule, we could state that vector AC is equal to AB plus BC. And in fact, we can check this result for the example we have here. Indeed, we had already found the vector AB. Remember, that's the vector 4, negative 2. And although we didn't write down what BC was, we did write down what CB was. Remember, that was the vector 2, negative 4. And so the vector BC is the opposite of CB, so its components will be -2, 4. And so if I write all of that out here, and I'll do that in gray, the vector AB has components 4, -2, and I'd be adding to that the vector BC, which remember is the opposite of this vector here, so it will be -2, 4. And I'll quickly write that, that's -2, 4. Adding those two together, we obtain the vector 4 plus -2, which is just 2. And so I'll quickly write that, that's 2. And -2 plus 4, which is 2. So the vector AC, which is the displacement vector going from point A to point C, has components 2, 2. And of course we can check our result here because we had said previously that the vector CA had components -2, -2. And since AC is the opposite of CA, its components 2, 2 are indeed the opposites of -2, -2. So this definitely works. But what I particularly like about this result here is that we don't have to stop at 2 vectors. Indeed, provided the letters on either side of the addition are the same, then they simply cancel each other out. What that tells us is that we can find this vector AC using a sum of as many vectors we want, provided the starting point of the first vector is A and the finishing point of the last vector is C. For instance, we could say that the vector AC is equal to AO plus OB plus BC. And in fact, we could also say that vector AC is equal to AO plus OB plus BC. So starting at point A, I go from A to O, from O to B, and from B to C. So my starting point was point A, and my finishing point was point C. And that's all that matters. Since, according to Chasles' rule, we can see that on either side of this first addition, we have the same letter, which is O, so they cancel each other out. So this becomes AB plus BC. And now on either side of this second addition, we have the same letter again, which is B. So those B's cancel each other out, which confirms that we get AC. And there we have it. There we go, everyone. That's it for this first tutorial on position vectors and displacement vectors. And so hopefully you're leaving this having a good idea and a good understanding of what a position vector is. Remember, a position vector's role is to tell us the position of a point relative to the origin. And of course, I also hope you leave with a good understanding of what a displacement vector is. Remember, the components of a displacement vector tell us how to get from one point to another. And there we go. All that being said and done, that's it for this tutorial.